Hi everyone! Welcome back to another Planetarium live stream. My name is Jessica. I am the director of the Planetarium, and with me tonight is a maybe not so familiar face since he's usually our voice in the sky, but I will let him introduce himself.
Hi, my name is Eli. I'm a physics and astronomy student at UMD.
So tonight's show is all about learning how we know things that a lot of people are just told as fact. All of these things had to be learned and figured out at some point, and Eli is going to tell us all about how that happened. In just a second, I'm going to turn it over to him. But if you have any questions, put them down in the comments. I will be looking out for those throughout the show. And anything that we don't get to right away, we will take time at the end and answer any of those questions that were missed. Yeah, I will turn it over to Eli.
Okay, let me just figure out the screen sharing here. Okay, does that look good?
Yep.
Okay, awesome. So how do we know? So the first bit is going to be kind of a survey of how things were discovered initially before the advent of things like telescopes or stuff like that, or space telescopes as well, because I think some of those are really impressive discoveries that were made long time ago. And then some of the end stuff is going to be things that we use today to learn about some bigger picture things. So before we start talking about discoveries, I know this looks kind of gross, but I just want to have some context for what I'm talking about in the future when we're talking about some of these discoveries. Basically, every discovery that was made a long time ago in astronomy was made with triangles. Because back then, trigonometry, which was just the math of triangles, was kind of the best understood math, and it was a really useful tool. So there are certain trigonometric functions that you can use to learn things about a triangle. So for example, if you want to take the sine, I don't know if you can see my mouse right here, but I'm circling the sine um, kind of bottom left. A sine of a triangle or the sine of an angle is the ratio of how big the opposite side is. So say our angle is the one highlighted down in the bottom left corner of the triangle. That is just the ratio of how big the opposite side is to the hypotenuse side. So basically, using these relationships, you can just find one thing out about a triangle if you know the other two things. So, for example, if the opposite side was 1 meter long and the hypotenuse side was 2 meters long, the sine of that angle would be 1/2. And then the inverse sine, which is another function that they knew about, would be 30 degrees. So not going to go into any math really going forward, but I just wanted to give some context for what I'm talking about. So let me bring my presenter view back up. So the first discovery that I want to talk about is the size of the Earth, because that was kind of the first really big astronomical discovery that was kind of set the foundation for further discoveries. So we know the size of the Earth really well nowadays, probably mostly because we have space telescopes that can leave Earth and take pictures of it relative to things that are far away, and we know how big they are. But when it was first discovered, it was kind of a groundbreaking thing. So around 200 BC, Greek astronomer and scientist Eratosthenes, I believe I pronounced that correctly, but I'll probably butcher a lot of these, devised a really clever experiment for doing this or for figuring this out. And this experiment relied on the fact that on the summer solstice, the sun casted no shadow in the city of Syene. So this diagram that I've made here shows Syene and the other town that he used, which was Alexandria. So if it casted no shadow, that meant that the sun was directly overhead, and that means that Syene lie on the Tropic of Cancer. So his experiment was, if he were to go, a far distance away to a city called Alexandria and put a stick in the ground there, would it also cast no shadow there? So he did this, and he stuck it in the ground, and he saw that it casted a shadow that was about 7.2 degrees. off of the stick. So with that, he could reason that the distance between Alexandria and Syene on the circumference of the Earth's surface was 7.2 degrees. And 7.2 degrees is about 1/50th of the whole circumference of the circle. So if he knew that 1/50th of the size of the Earth was that distance, if he knew that distance, he could know the whole size of the Earth. So I think this is really funny too. He actually hired someone to walk that distance and to measure how far it was, which, mind you, is 800 kilometers, so very, very far distance. And he reasoned that, okay, well, if 800 kilometers multiplied by 50 or 800 kilometers was the distance, and then you multiplied that 50 to make the whole circumference, or not 50 rather, 100. So if he multiplied that by 100 to go around the whole circumference of the circle, he would have the circumference of the Earth, and it turned out to be 80,000 kilometers. And that is really close to the real number, because the real number is 80,060 kilometers. So he was really close, actually just within 1% accuracy to finding the circumference of the Earth. So now we know that. We have this information at our disposal, and it was used by astronomers in the future to calculate more things.
I also want
Kind
to
of,
point out that at this point with the ancient Greeks,
yeah,
they knew the earth was round.
right, yeah. Some people later on decided to question this knowledge, but no, yeah, they knew, um, and they did a couple things to do that. There were some experiments. I remember one involving a lighthouse, but yeah. So I that's just it blows me away that somebody 2,000 years ago had the wits to put this together. So next we have the size of the moon. So Aristarchus of Samos saw that the size of the Earth had been found, and he wanted to use this to find the size of the moon by looking at eclipses. So he correctly reasoned that when they saw an eclipse that was caused by the moon passing behind the Earth's shadow and going directly behind the Earth relative to the sun, and it not receiving any light. What he didn't reason correctly is that the light kind of makes an angle when it goes through. So he thought that the shadow of the Earth was bigger than it actually was, and this led to a little bit of inaccuracy in his estimation, but not like really volatile in any way. So the diagram I drew above here is what he thought the situation to be, and the diagram I've drawn below is what it actually is. And obviously scales are all messed up just so I could display it on a computer screen. But there is kind of the basis for his experiment. And what he did is he timed the amount of time it took for the moon to pass through Earth's shadow, and then he timed how long it took for the moon to move one of its own distances. And he found that it took the moon 2.6 times longer to travel behind Earth's shadow than it did to travel one distance, or that the shadow was 2.6 times larger than the moon itself. So with that, he could just divide the size of the Earth by 2.6, and he would have the size of the moon. And it's pretty close. Like I said, his how he thought of the experiment kind of made it go a little wonky, but he got it to within 9% accuracy, which I still think is absolutely remarkable. Didn't have a telescope, very limited math at his disposal, and it was just really, really like impressive that somebody back then had the intellect to do this, especially when he knew so little about the solar system and space. But I guess it had to start somewhere. So, okay, now we know the size of the moon. And the next step was finding the distance to the moon. And this one is insane to me. This is the most impressive one, in my opinion. So Hipparchus, who was also kind of the inventor of trigonometry, saw that if you're in one place on the Earth and you look at the moon, you can see this star behind it. So let's look at the left image right now. Say that he's in, Alexandria in that image, and then he moves to somewhere in England, and he'd see the image on the right. So he saw that, as you move across the Earth's surface, the position of that star changes behind the moon because the location you're seeing the moon at changes, or the angle you're seeing it at, rather. So he thought he could use this to his advantage when trying to find this distance, and he kind of invented something called the parallax method, which is still used today. So when he moved across this distance, he saw that this star changed its position. Now we have both of the positions that we would see next to the moon here, and he measured the distance between those two, or the angle between them, and then he created this triangle down here between points 1 and 2. And the angle seen between the stars is also the angle you would see in that triangle. So then, through some trigonometry that pretty much he invented, he was able to solve for the distance to the moon with that angle, just by dividing it by 2 and making it a right triangle. And this method is still in use today, and in fact, astronomers use it to find the distance to nearby stars, which we will also talk about later. Yeah, again, just absolutely amazing. This one kind of boggles my mind, especially because the number of that angle was 0.3 degrees, which is such a small amount of like space in between those two stars to measure without astronomical tools. And he got it really close. He got it to within 17%. So again, we're seeing some error propagation, but for 250 BC, I don't really think you can fault them.
Yeah, and I know you've said it, but just to point it out again, that angle is so, so small. It's exaggerated in this picture.
Oh, yeah, like a lot.
Very exaggerated how much the star appears to shift. It's a very
Right.
small amount.
Yeah, it's incredible. Like, I don't even think I could draw a diagram that precise, let alone figure anything like that out. So again, it's super amazing. So next, Aristarchus took the reins again, and he wanted to find the distance to the sun. This one was a lot easier after the distance to the moon had been found. So basically, he realized that when we see a half moon, or the technical term is the third quarter moon, that the reason we're only seeing half of the moon illuminated is because we're making a right triangle with the sun, the earth, and the moon, as you can see here in this diagram. So since the sun is shining, directly sideways at the moon, from Earth's perspective, we'd only see half the moon. So he waited for this to happen, for us to see a third quarter moon, and then he measured the angle between the moon and the sun in the sky. And that is the angle that we see denoted here. It's 89.93 degrees. He actually measured it to be about 87, but that's because, again, he measured it with his naked eye. And that took away a little bit of accuracy, but kind of the concept is still the same. So he could use trigonometry again, solve for that triangle. He used the cosine function of 89.93, which is equal to the distance to the moon divided by the distance to the sun. And then if you just multiply the distance to the sun on both sides and then divide both sides by the cosine, you get that the distance to the sun is equal to the distance to the moon divided by cosine of 89.93, or in his case, 87. And he found it to 14% accuracy. So again, absolutely amazing. And really cool that, after all this work had been put in to find the distance to the moon, it was just as easy as realizing that, a half moon is a perfect right triangle. So kind of the knowledge that they had to have of how things were working before they even really knew how far they were or where they were. It's really impressive. So this next one is probably my favorite, and it is the size of the sun. So this one only comes about because we live in the perfect spot. If the Earth was any closer or further, or the moon was any closer or further, this wouldn't work, because this discovery is hinged upon the fact that during a solar eclipse, the moon perfectly blocks out the sun. But luckily for us, it does. Very luckily, actually. And Aristarchus saw this, and he reasoned that, okay, well, if the ratio of the size of the sun to the size of the moon or they completely block each other out, then you can just relate that to the distance to the sun over the distance to the moon. So as seen in this diagram above here, I didn't note any angles or anything like that, but if you were to construct a right triangle out of that, the you could put this comparison together, and he was able to find the sun that way, and he found that the sun was much larger than the Earth, which is definitely true. But these kind of errors or inaccuracies that had led up to this point led to some significant error. But this was important because in knowing that the sun is way bigger than the Earth, that kind of set the stage for reasoning that things would go around the sun. Because before that, they didn't know how far the sun was, and if it was really far, and or really close and reasonably small, they would think that things would go around the Earth. But in learning that the sun is much larger than the Earth, it kind of got people thinking that maybe things go around the sun rather than things going around the Earth. So that's where that one led. I also very much like this next one, actually. I wrote a report on this next one for one of my classes. So on the left here, you are looking at Ole Romer, who was a Danish astronomer, mainly active in the kind of mid 1600s. And he was working at the Paris, I believe it was the Paris Observatory, and timing how long it took for one of Jupiter's moons to orbit Jupiter completely. And so he would he would measure the amount of time between when it would eclipse. So when it would, come out and then go back behind. So over a period of years, he took all these measurements, and he found that when Earth was at the closest distance point, labeled on the right there, it would be about 11 minutes. The time for the eclipse to happen would be about 11 minutes shorter than the average, and when it was at the farthest distance, it would be about 11 minutes longer. So after some thinking and trying to figure out what was going on, he decided that, or he thought that the reason was because the light took more time to travel to Earth when it was at the farthest distance and less time when it was at the closest distance. And this was kind of a revolutionary thought at this time because previous to this, any attempts to prove that light traveled at a finite speed had come up empty-handed. The most notable one is that Galileo and another man stood on hilltops separated by about a mile, and they both had lanterns. And one of them would open the lantern, and then the other one would open their lantern as soon as they saw the light. And as you can imagine, that probably didn't go too well because light travels, at an insane speed, 300,000 meters per second. Or no, is that right? 3 million meters per second. I'm blanking.
Yeah,
I think
it's
it's 300.
300,000 kilometers per second.
There we go. Thank you. 300,000 kilometers per second. So that's, when we see light, when we turn on our light switch, it happens immediately. And it doesn't happen immediately, technically, but it looks like it does because it just goes so fast. So this was kind of a groundbreaking thought at the time. And then after he had kind of thought up this consequence, another famous astronomer, Christian Huygens, measured the speed. He did the math and put in the work, and he found it to within 70% accuracy. I think he got somewhere around like 212,000 kilometers per second, something like that. So this was a really big one, just because this one kind of opened a new door for physics as well, and how light works, and it became a very popular field of study. And then 50 years after Ole Romer and Christian Huygens put this together, the speed was confirmed by another astronomer named James Bradley, and he did it by looking at how light interacts with telescopes. So that was, Romer's thought process was proven, and I really like that one as well. All right, so now this one is how do we know the distance to nearby stars? We kind of already talked about this one, except we talked about it with the moon. One of the methods of finding the distance to relatively nearby stars, I mean, a lot of stars are really far away, but for the most part, nearby stars, we can find it using the same method. So in January, we would see the picture on the left, and the red dot is the star in question, the nearby star. And then in July, we would see the image on the right. So astronomers measure the angle between those two positions, and those stars behind it are stars like way, way, way behind the star. So that's kind of the frame of reference. So they measure the angle between those two positions, and by this point, we know how far the Earth is from the sun. So again, you can just make another triangle and solve that, and that's how we know how nearby stars are. Farther stars, it gets more complicated, but Hipparchus's method of finding the distance the moon lives on. And now we'll go to the next one. How do we know how far galaxies are? This one is really cool as well. So over a long period of time, astronomers have observed events a lot, some of those being supernova. And we know with, relative comfort how bright these supernovae should be. And so when we're looking at a galaxy and we see a supernova happen, we can compare how bright we saw the supernova to be with how bright it should be, and that gives us an idea of how far the galaxy is. So the brightness of an object follows what's called the inverse square law. So that's what's on the bottom right here. So if I were to move twice as far away from a light source, I would do the brightness equals 1 over 2 squared, which is 1 over 4, and the light would be 1/4 as bright. Or if I move 3 times as far away, it would be 1/9 as bright. 1/4 would be 1/16, and so on. So obviously the numbers are a lot bigger than 1/9, but same rule applies. When we see this, we know how bright it should be. We know how bright it actually is based on the pictures that we take, and we can figure out how far the galaxy is like that. And then the last one, I like this one specifically because it is referenced in Star Wars, and Star Wars is near and dear to my heart. So how do we know where black holes are? So black holes are kind of a tricky thing to look at in general because you can't really look at them by their nature. They don't really give off, well, not really, they don't give off any light or any context clues. And so we kind of have to infer where they are based on the motion of objects around them. So when I played this video, and Jessica, could you tell me if this is playing all right? Does that look good?
Yep, looks good.
Okay, cool. So that kind of reticle, that cross in the center of the image, is the supposed position of a black hole. And the reason we think it's there is because when we watch these stars orbit this, invisible center of mass, and I'll play the video again, it looks like they're orbiting something, and something with a really, really strong gravitational influence. And since we can't see it, the object isn't giving off any light, we can infer that there is a black hole there. And this is actually what we see at the center of the Milky Way. So when we look really close and we look at the stars directly, in the vicinity of that black hole, we see that there's this motion around what appears to be an invisible center of mass. So that's how we know where black holes are. This video is really cool. It kind of like tracks their position over a period of 10 years, or just over 10 years. All right, and with that, I am finished up.
Very cool. All right. Well, if you have any questions, now is a great time to leave them down in the comments. While we wait and see if you do have any burning questions, I want to remind everyone, or maybe let you know if you don't know about it, that the Planetarium is doing our very first giveaway. If you watched the Crew Dragon launch the other week, you may have noticed that this little glittery dinosaur hitched a ride up into space. And we have 2 of these, just like the dino that went to space, and we want to give it away to our lovely viewers and followers. So what you're seeing is the web address that has all of the information. It's also linked in the description for the video. You can just go click on that. But the general idea is we want you to design a mission patch and submit your design to us, and you will then be entered to possibly win one of these two dinos. We will be randomly drawing them during our show on July 1st. So all of the details are there. We're very excited to see what you come up with. And yeah, I'll leave it up for just a second. Again, the link is also in the video description, so you can always go find it there. But all right, I do not see any questions. But Eli, thank you. That was awesome. And I know, I think it's really cool to see just kind of how crazy smart some of these people were.
It makes me insecure. Like
A
it
little
really
bit.
does. Like just the things that those people like thought up. Like it's not like they were doing like super intense math or anything, but just like that spatial
Yeah,
awareness and like understanding. It's just
it's amazing.
yeah,
And like
it's
having to
baffling.
invent new mathematical
Right.
methods.
Yeah.
I mean, like, yeah, no, I'm just gonna invent trig so I can
Yeah.
solve this problem.
Yeah, and the other thing is like they didn't have. I mean, obviously, it's not that this needs to be said, but they didn't have calculators, so they had to figure out what those values would be, you know, by kind of like times tables they had, and like okay, if 85 is this and 86 is this, 85.5 must be somewhere in between
Yeah,
there. So it's like
it's crazy.
it's insane. It was a lot
But
of fun making that.
yeah. All right. Well, coming up over the next week on Saturday, we are doing, what are we doing Saturday? Northern Lights. Yes, we're doing a show all about the aurora, what it is, what causes it, give you some tips to help you see it yourself if you'd like to. And then next week on Wednesday, we are going to do a tour of the moons of the solar system. So we've gone and visited the planets and stopped at a couple of moons, but we're going to do a whole show just focusing on moons because there's a lot of them and there are a lot of really cool ones in our solar system. And then next Saturday, we are going to do kind of a little tour of what are called the Messier objects. These are things like star clusters, galaxies, nebulae that you can pretty easily find up in the nighttime sky, and you don't need like super fancy telescopes or equipment to do it. You can see them with a decent powered binocular or kind of, a smaller telescope. And so we're going to tell you all about kind of what these objects are and some of the good ones that you can try and find this summer. But with that, we will wrap it up. Thank you again, Eli, for an awesome show. As always, if you want to rewatch anything or catch anything that you missed, all of these are up on our YouTube channel as well as on the videos page of our Facebook page. But thank you everyone for joining us. We hope you join us again and have a great evening and the rest of your week. Bye.